We've touched on what radicals are in relation to index numbers, but did you know that there are rules that apply to radicals just like there are rules that apply to indices? Hi everyone and welcome to Sneezy Teachers, and today we're going to be looking at the rules for radicals. Before we start on today's lesson on rules for radicals, let's quickly review some important vocabulary. This symbol is called the radical symbol or the radical sign. The number inside the radical symbol is called the radicand. The little number outside the radical symbol tells you what root is being taken and is called the index. A radical expression is any expression that contains the radical symbol. Finally, an irrational number is any number that can't be expressed as a ratio between two integers. Some radical expressions are rational, like the square root of 4 or the cube root of 27, but some are irrational. The square root of 3 is an example of an irrational radical expression. When a radical expression can't be evaluated to give you an exact answer and is left untouched, it is called a SURD. If you're ever asked to leave an answer in exact form, that's what this means. To leave it as a SURD rather than to calculate it and get an approximate answer. With indices, the number being multiplied is called the base. The little number written in superscript generally tells us how many times to multiply the base by itself, although this definition can get a little hairy when dealing with negative or fractional exponents. But we call this little number the power, or the exponent, and also the index. When a number is written in index or exponential form, that means it's written in an exponential expression where we have a number raised to a power. 2 cubed, for example, is an index form, but the number 8 by itself is not. Think you've got it? Great! Looks like we're ready to power through. The most important thing you should know about radical properties is that the laws for radicals are actually just the index laws in disguise. This one is actually just basic algebra. Suppose we had the square root of 2 plus the square root of 2, and we were asked to simplify this in exact form. If you think of the square root of 2 as an unknown variable, which it kind of is, given that it's an irrational number, this is actually fairly simple. What do we get if we have x plus x? We'll have 2x. So what do we get if we have the square root of 2 plus the square root of 2? We'll have 2 square roots of 2, so it'll be 2 root 2. Note that adding 2 square roots together doesn't cancel out the root function the way multiplying does. The square root of 2 multiplied by itself would cancel out the radical symbol, because it would essentially square the square root. Adding square roots won't do that. Also, for this to work, the radicands and the index numbers have to be equal, because you're basically combining like terms. So, for example, 5 times the cube root of 3 minus 2 times the cube root of 3 can be simplified to 3 times the cube root of 3, because these are like terms. But if you had 5 times the cube root of 3 minus 2 times the cube root of 6, this wouldn't work at all. These are unlike terms and can't be combined. The law for multiplying and dividing radicals goes like this. When multiplying two radical expressions with the same index, we can combine them as one radical expression, where the radicand is the product of the two original radicands. So for example, the square root of 2 times the square root of 50 is the same as saying the square root of 2 times 50 equals 100. This is handy because while the square root of 2 and 50 are irrational numbers, by using the product rule, we'll have the square root of 100, which is a nice, neat 10. Why does this work though? Well, let's try converting them into index form and see what we get. The square root of 2 is 2 to the power of a half, and the square root of 50 is 50 to the power of a half. So we'll have 2 to the power of a half times 50 to the power of a half. Wait, this looks familiar. It's the index law for powers. If a to the power of n times b to the power of n is equal to a times b to the power of n, then 2 to the power of a half times 50 to the power of a half should be equal to 2 times 50 to the power of a half, which is 100 to the power of a half, or the square root of 100. So you see, the product rule for radicals is basically just the index law for powers inverted. It works the same way for dividing radicals too. Say we have the cube root of 27 over 8. This is the same as saying the cube root of 27 over the cube root of 8, or in other words, 3 over 2. And again, if we convert it into index form, we'll see the index law for powers in action. Some radicals are irrational but can still be simplified. This is useful when dealing with large numbers because sometimes you want to leave an exact answer but you don't want it to be a big and bulky radicand. For example, suppose we're given the square root of 72. This is definitely an irrational number between two perfect squares. If we put the square root of 72 into our calculator, we'll only get an approximate answer. So what could we do if we wanted to keep our answer exact but using simpler terms? Well, let's look at the product rule for radicals again. If we have two radical expressions with the same index multiplied together, we can combine them into one radical expression. Here's a thought. What if we tried doing the reverse of that? What if we want to split one radical expression into two smaller ones multiplied together? If one of the smaller radicands is a perfect square, then even if we can't square root 72, we can square root part of it. Let's try it. The square root of 72 can be written as the square root of 72 times the square root of 1, the square root of 36 times the square root of 2, the square root of 24 times the square root of 3, the square root of 18 times the square root of 4, the square root of 12 times the square root of 6, and the square root of 9 times the square root of 8. Out of all of these examples, two of them stand out, this one and this one. 36 is a perfect square and can be square rooted, just like 9. If we go with 36, we'll have 6 times the square root of 2, or 6 root 2. If we go with 9, we'll have 3 root 8. These are both correct answers, but 6 root 2 is simpler. The square root of 2 is a simpler surd than the square root of 8. And actually, if we try to break down the 8 like we did with the 72, we would eventually get 6 root 2 anyway, because the square root of 8 can be written as the square root of 4 times the square root of 2. The square root of 4 is 2, so we would end up with 3 times 2 times root 2, or 6 root 2. So, to put a radical into simplest form, what you need to do is find the largest factor of the radicand that is a perfect square, or whatever the index asks for. Let's try another example. Let's try the square root of 48. The square root of 48 can be written as root 48 times root 1, root 24 times root 2, root 16 times root 3, root 12 times root 4, and root 8 times root 6. There are two perfect squares we can use, but 16 is the biggest one. We would have 4 root 3. Now, sometimes you might have a bit of trouble getting your radical into simplest form on the first try, but that's okay. All you have to do is keep double checking your answer and making sure that it's already in the simplest form it can be. So, for example, suppose you decided to use the square root of 4 instead of the square root of 16. You would get 2 root 12. Now, if you stopped here, you'd be in trouble, but if you examine your answer, you'll see that root 12 can be simplified further into root 4 and root 3. The square root of 4 is 2, so you would end up with 2 times root 3, or 4 root 3. So we got there in the end. It just took a little longer because we had to simplify twice, that's all. You'll normally only be asked to simplify square roots, but sometimes there'll be cube roots too. In this case, you can use the same rule. The only difference is now you're looking for perfect cubes instead of perfect squares. So for example, if you were asked to simplify the cube root of 16, after listing the factors of 16, you'll see that out of all the possible radicands, 8 is the only one that is a perfect cube. The cube root of 8 is 2, so you would get 2 cube root 2. So to recap, to put a radical expression in simplest form, the first step is to think of or list all the factors of the radicand. Then, pick the largest factor that you recognize as a perfect square, or if it's a cube root, then you're looking for a perfect cube, and so on. Finally, after calculating the root of the factor you chose, double check your expression. Make sure the radicand is the smallest it can be. Check that there aren't any more factors that it can be split into and simplified further. That's it. Try simplifying a few radical expressions of your own. Look for like terms to combine when you're adding and subtracting radicals. If you're multiplying or dividing, sometimes it's better to combine two radicands together, and sometimes it's better to split one into two. Use the product rule to make sure that all your answers are in simplest form. The last thing we'll need to worry about is when the denominator of a fraction is a surd, but we'll cover that in the next video. Until then, keep up the hard work, and I'll see you next time at Sneezy Teachers. Bye!